Good morning, good afternoon, and good evening, fellow physics students. Hope you guys woke up with 5 fingers on each hand. If not, a sufficient amount is good enough. As long as you're able to write with them, as long as you're able to keep up with the exercises I'll be going through today, you'll be just fine. Okay, let's start. Number 1. The ball and string system shown on the left, this is the left, is placed on a frictionless ground, meaning the ground that the ball is in contact with has no friction. What direction is the centripetal acceleration? If v equals 10 meters per second, r equals 6 meters, and m equals 19 kilograms. Let's go ahead and start there. Okay, so got a ball. This is going to be 6 meters. The velocity here is going to be equal to 10 meters per second. And the mass of the ball is going to be equal to 19 kilograms. Now, if you can recall really quickly what centripetal acceleration is, if something is revolving around something at a constant velocity, there is going to be some acceleration. You might ask why. The acceleration is equal to change in velocity over time, right? And there is no change in velocity. But alas, there is. There is a change in velocity. And the change is going to be in the direction, not the magnitude of the velocity. Oh dear. Let me see. Because of that, it's going to keep on changing like this as it revolves around the object. Like that. So if we are able to deduce, if you look at this like this, then you can probably predict which way acceleration is going to be going. It's going to be going like this, like this, like this. You can imagine it like you're at the center. You're holding this ball at the center, and you're constantly pulling on it this way to keep it revolving around you, stuff like that. Hope that makes a sufficient amount of sense. With that stated, let's go ahead and see if we can find centripetal acceleration. Really quickly pause the video and see if you can recall the formula for centripetal acceleration. Okay, hopefully you've paused the video. If you haven't, that's okay. Well, no, it's not okay. You should try. You should definitely try. But if you haven't, here's the formula for centripetal acceleration. Centripetal acceleration is equal to the velocity squared over r. R being the radius between the center and the object. So if we use this, we can calculate that the centripetal acceleration, in this case, is going to be 10 meters per second squared over the radius, which is 6, which we're going to get 100 divided by 6, which for right now, this is good enough. This is going to be equal to the centripetal acceleration that you should have gotten. Now, what about mass? Well, in this case, mass is not needed because this is the formula for centripetal acceleration. All we needed was velocity and radius. Okay, cool. All right, now what about part 2? Part B. Part B says that the radius is still the same, the velocity is the same, and the mass is changed. The mass is now 18 kilograms. What is the centripetal acceleration now? Pause the video, see if you can find a solution. My apologies, let me move that. Okay, so the answer is going to be the same as the last one, which is going to be 100 divided by 6. And the reason for that being is because the centripetal acceleration is just equal to the velocity squared over r. It does not change with the mass, at least not in this case. There will be a case in which something will change because of mass, but it will not be because of centripetal. It will not be centripetal acceleration that changes. Okay, what about C? The velocity now, the velocity of the ball is still 10 meters per second, but now the radius is 12 meters. The mass is going to be 10 kilograms, which if we're just finding centripetal acceleration, is going to be going to be unnecessary to keep this. But let's go ahead and find centripetal acceleration. Centripetal acceleration in this case is going to be equal to 10 squared divided by the radius, which is 12. So it's going to be equal to 100 divided by 12 in this case. So for both of these, we got 100 divided by 6. And for this one, we got 100 divided by 12. Let's see what we can get for the last one. The velocity is going to be equal to, in this last case, is going to be equal to 20 meters per second. And the radius is going to be equal to 6 meters. Mass is going to be equal to 10 kilograms. 10 kilograms. What is the centripetal acceleration? It's going to be equal to. Go ahead and solve it if you know how to solve it. Okay, I'll go ahead and do it. It's going to be 20 squared divided by 6, which is going to be equal to 400 divided by 6. So for this one, we got 400 divided by 6. All right, now let's see. By what factor does centripetal acceleration change when velocity doubles? Okay, let's see. If we use let's go ahead and use some arbitrary values. Let's say AC1 is going to be equal to V squared over R. And now let's say AC2 is going to be equal to, okay, so velocity here is going to be equal to V1, and R here is going to be equal to R1. Velocity here is going to be 2 times our first velocity, so 2 times V1, and our radius here is going to be the same. Let's see what happens. V1, 2V1 squared divided by R1, which is going to be equal to 4V1 squared divided by R1. So by how much does this, how much greater is AC2 compared to AC1 is basically what I'm asking here. If the centripetal acceleration, if the velocity doubles, what happens to centripetal acceleration? And let's see. If we could put this in terms of AC1, which is going to, if we bring it up here, 4 times V1 squared divided by R. Does this look familiar? This right here is the same as this one right here. So we can go ahead and convert that to 4 times AC1. So when our velocity doubles, our centripetal acceleration will quadruple. Now let's see what happens to our centripetal acceleration when the radius doubles. Now when the radius doubles, we're going to have the same approach. V1 is going to be, our velocity is going to be equal to V1, and our radius is going to be equal to R1. In this case, AC1, centripetal acceleration 1, is going to be equal to velocity 1 squared divided by R1 squared. No, not squared. And let's see, AC2 is going to be when velocity is equal to V1, and radius is going to be 2 times our first radius, so 2 times R1. And that's going to be equal to velocity 1 squared divided by 2R1. So let's see if we can put this in terms of AC1. So if I factor out 1/2, we get velocity 1 squared divided by R1 is equal to AC2. And this looks a lot like this. Well, it is exactly this. So we can go ahead and replace this with that. 1/2 AC2 is going 1/2 AC1 is going to be equal to AC2. So when our radius doubles, our centripetal acceleration halves in this case. And our last question, what direction is centripetal acceleration going? Well, as I've denoted in the beginning, hopefully you can recall, the centripetal acceleration, there is no change in the magnitude of the velocity. The velocity is constant, but there's a change in the direction. And if you can imagine, we have to keep on changing the velocity like this, like so, in order to change its direction. Something like this. But at the end, the acceleration is going to be towards the center of the object, of wherever it's pivoting around, whatever it's revolving around, which in this case is going to be the center. So that is going to be the direction of centripetal acceleration. It's going to be towards the center. In this case, it's going to be downwards. Up here, it's going to be downwards. But in general, centripetal acceleration is towards the center. All right, on to Okay, on to set number 2. The ball and string system shown on the left. That's not English. The ball and string system shown on the left, and I meant to write is vertical. So the ball and string system shown on the left is vertical, meaning, imagine you're holding, this is your hand, and you're holding some kind of ball, like this, and you're swinging it around like this. That's what I mean by vertical. It's no longer on the ground. It's not flat on the ground. That would be horizontal. If you can imagine that this is the ground. It's no longer horizontal. This is vertical. So, this is vertical. Draw the free body diagram. Go ahead and take an attempt, and come back shortly. Okay, awesome. All right, so position 1. Let's go ahead and draw the free body diagram for position 1. For position 1, the velocity is going to be going this way, which I'm going to denote up here instead of writing it down here and confusing it with one of my forces. So let's see. This ball is going to be affected by a couple of things. One thing is going to be obvious. It's going to be gravity. The other thing is going to be centripetal force. Or in this case, this is going to be more centrifugal force, but let's call it FC. It's going to be the same amount, but in the opposite direction. Okay. And anything else? Well, in most cases, there's also going to be tension force. There's going to be a tension force that is brought by this string. So that's number 1. Number 2. We are now in this position. Velocity is going this way. Velocity is, where can I write? Well, I'll write it up here. Velocity is going this way. Let's see what forces are on this ball now. Well, gravity is obviously one of them. We're going to have tension. And then we're going to have centripetal or centrifugal force. The reason I keep saying centripetal or centrifugal is because they're equal. But the word centripetal literally means center seeking, seeking towards the center. So if it's a center seeking force, is going towards this way. The opposite but equal value is going to be centrifugal force. The opposite and equal amount is going to be centrifugal force. Centrifugal means fleeing from the center. That's what centrifugal force means. But in this case, we're going to have we'll just denote this as FC. It makes this really simple to think about when we do it this way. Number 3. In position 3, we have ball. The velocity is going to be going to denote it right here. The tension is going to be going this way. The gravity is going to be going this way. And also the centrifugal force is going this way. And lastly, but not leastly, if that's a word, is going to be position 4. Which has the velocity going this way. We have gravity, we have tension, and we have centrifugal force. Okay, these are the free body diagrams for each one of them. Find an equation for tension in each position. Okay, let's see. Well, tension, let's go ahead and denote this as the force, the net force. The net force in this case is going to be well, if this ball is not going anywhere, then the net force in the vertical direction is going to be equal to 0. It's going to be equal to 0 because the ball is not going anywhere. So we can write it like this: tension plus gravity minus force centrifugal is equal to that. So let's solve for tension now. If we just isolate tension, tension is then equal to force centrifugal minus gravity. Which makes sense if you can imagine swinging this ball. What you would feel is at the top it will feel the lightest, and at the bottom it will feel the heaviest. If you've ever been on a roller coaster, you experience something very similar. When you're in a roller coaster and it's going in a loop-de-loop, at the very bottom, at the very top you feel almost weightless, and at the very top you feel almost weightless, and as you reach the bottom you feel about as heavy as maybe a really dense sponge. In other words, then you have an incredible amount of force going down on you at one time, but at the top you have very little net force, and that is you can mathematically prove that. Well, physically prove that, if that's the right term. You can mathematically prove it with this equation here. Position 2. Let's go ahead and solve for tension. Tension is going to be straightforward, is equal to force centripetal net force, if it's not moving in this direction, or if it's not accelerating in this direction, is going to be equal to 0. It's going to be equal to tension minus force centrifugal. So tension is equal to force centrifugal in this case, or force centripetal. They're equal to the same amount, but not in the same direction. There's a distinction. Just remember that distinction. Yeah, why isn't gravity in this? Well, it's not in the same direction. Remember, when we're dealing with problems, we want to break them down into axes that we can use. If we're working with one-dimensional problems, then we want them in one direction, in one dimension, which is going to be these dimensions. If we're working with two-dimensional problems, then we want them in one of two dimensions. One of two dimensions. This makes it really easy to work with. And in this case, the the two dimensions that we have are y and x and y. And in the x direction, the only forces that are present are tension and force centrifugal. And when we put them together, tension minus force centrifugal is equal to 0, because this is not moving, and therefore tension is equal to force centrifugal. Okay, so let's see. Point 3, we're at the bottom. Okay, so let's see if we can solve for this. T is going to be equal to force of gravity. Oh wait, no, let me stop myself. Force net is going to be equal to 0, which is equal to tension minus force of gravity, or I'll just write this as G, minus force centrifugal. And if we solve for T, we get that tension is equal to force centrifugal plus gravity, which this also mathematically proves why we feel so heavy at the bottom of a roller coaster. At the bottom of a roller coaster, as you come down towards the bottom, right at this bottom right here, you're going to feel this force that's going to make you feel heavier, and this is basically it, except it's a little different because you're not attached to a string. There's a little bit, it's a little different of a system, but we'll go over that problem in the future, and I'll explain why it's different, but this is the general idea. So for number 4, let's see. Number 4, we have tension going this way. I don't know why I didn't write that down. Tension going this way, force centrifugal going this way, gravity going this way. Let's see, F net in the horizontal direction is going to be equal to tension minus force centrifugal. And we see that tension is equal to force centrifugal when we solve for it. Okay, very cool, very cool. Okay, so let's see. What position would the tension be the greatest? Okay, let's see. So how would you solve for this? So we can, if you want to make it, if you want to solve for it quantitatively, what you can do is assign values to force centripetal and gravity. So if you give force centripetal maybe 100 newtons and gravity equal to, so let's say 50 newtons, right here, tension will be equal to 100 newtons minus 50, which is equal to 50 newtons. Tension right here will be equal to 100 newtons. Tension right here will be 100 plus 50, which is equal to 150. And tension right here is going to be equal to 100. So we can see quantitatively that this one is going to be the greatest. When we're at the bottom, that's when tension is going to be the greatest. And what you can also do, if you want to solve it, I guess, qualitatively, if that's the right word, you can imagine the roller coaster analogy that I gave you. At the top, you are almost weightless because centrifugal force is pushing you upwards, but gravity is pulling downwards. And the weight that you feel is just going to be the difference between the force centrifugal minus the gravity, if that makes any sense. If that doesn't make any sense, just look at these equations, imagine it, feel it. That's basically it. Bada bing, bada boom. Next problem. All right, so this is question number 1 from the homework. I do have the answer key right here, but that really doesn't matter unless you can arrive at the correct solution. So let's go ahead and see what we can do with this. A large centrifuge, like the one shown below, is used to expose aspiring astronauts to accelerations similar to those experienced in rocket launches at atmospheric re-entries. What angular velocities in radians per second is the centripetal acceleration 10 g? At what angular velocity in radians per second is the centripetal acceleration 10 g if the rider is 11 meters from the center of rotation? All right, so one thing I want to explain really quickly is this right here, angular velocity. Angular velocity. Angular velocity is basically, okay, so regular velocity is going to be equal to v, which is meters per second, or distance over time. Now, angular velocity is denoted by this symbol lowercase omega, and this is going to be equal to some angle with respect to time, some change in angle over some respect to time. And what this means is, in this case at least, is going to be, if we start here, right? If we start here, and we end up here, and this angle right here is 180 degrees, and the time it took us was, let's say, 6 seconds, then our angular velocity is going to be equal to 180 degrees divided by 6 seconds, which is going to be equal to 30 degrees per second. But you will not see this. This degrees per second is not the SI unit for angular velocity. Rather, it is radians per second. And what that is 1 radian. 1 radian is going to be okay. So this is. I'll give you this conversion really quickly. So you have this circle right here. We start from here, and we end up here. This angle right here is equal to 180 degrees, which is also equal to pi radians. Is equal to pi radians. You can think of it this way: with this angle, what multiple of radius do we need to get this perimeter? And for this, at least, okay, so let me give this for more clearly. Perhaps a circle will make more sense. Circle, which is equal to 360 degrees, which is equal to 2 pi radians. So the radian can be thought of as what multiple of radius do you need to get the perimeter? And if you remember, the formula for a circle, at least the circumference, is equal to 2 pi times radius. So 2 pi amounts of radius, and 2 pi multiples of radius. Radius times 2 pi in this case. Half of this circle, which is going to be right here, is going to be equal to pi radians. And hopefully that helps you understand the term, the meaning of radians. So let's see. So what we're looking for is yeah, okay, so let's see what we can work with this. The centripetal acceleration we're given is equal to 10 G's, which is just going to be equal to 10 times gravity, which is going to be 10 times 9.8, which is going to be 98 meters per second squared. If the rider is 11 meters from the center of rotation. So let's go ahead and write down our formula for centripetal acceleration: v squared over r. And let's see if we could solve for something. Okay, so we have radius, we have acceleration, centripetal acceleration. Let's see if we can solve for velocity. Let's see what we can do with that. So 98 is equal to velocity squared over 11 meters. Go ahead, and 98 times 11, the square root of that is going to be equal to the velocity. 98 times 11, square root of that, is going to be equal to velocity. 32.8329 which I'm going to denote right here. Velocity is equal to 32.833 meters per second. Okay. Okay, let's see. Okay, so we know that the entire revolution of a circle, that is going to be equal to 2 pi radians. That is that. So what we can do is, with this, how long does it take to traverse the entire circle, or the entire circumference in this case? So let's calculate the circumference. If we can calculate the time that it takes to traverse the entire circumference, then we have 2 pi radians over t, which is going to be equal to angular velocity. So let's go ahead and solve for t. T is going to be equal to how long it takes to traverse the circumference with the given velocity. So we have 11 meters, 2 pi r, 2 times pi times 11 divided by 32.833. And t is equal to 2.105 seconds. So with that, let's go ahead and divide 2 pi radians divided by this time. 2 pi radians divided by 2.105 seconds. And here's a quick question for you. What are the units going to be for angular velocity? Go ahead and pause the video and give it a shot. The units are going to be radians per second. 2 pi is some value, 2 times pi, divided by 2.105. What we're going to get is 2.985 radians per second. Let's see, is that our answer? Oh snap, would you look at that? We got the right answer. That's awesome. That's cool. That's pretty cool. Okay, now for the second part of this problem, B, the rider's cage hangs on a pivot at the end of the arm, allowing it to swing outwards during rotation as shown in the figure. At what angle in degrees below the horizontal will the cage hang when the centripetal acceleration is 10g? Hence, the arm supplies centrifugal force and supports the weight of the cage. Draw a free body diagram to see what the force is. To see what angle theta should be. Okay, so for this, I would like to give you an example. Find some purse around your house. See if you can grab it. If you don't have a purse, go find a purse and steal it, because you will need it for this example. Go ahead and hold it out like so. Let me see if I can. Give me a second. Okay, this camera right here. Oh, hold on. Okay, next camera. Okay, this one right here. Okay, this is my man purse right here, and for this example, I want you to notice something. If we draw a free body diagram for right now, what's going on is this has the force of gravity is pulling this downwards, and my arm is sustaining it upwards. Therefore, the net force is going to be equal to 0. It's not moving anywhere. So we got that going. Okay, so let's see what happens. So right now, the angle with the horizontal is going to be 90. It's going to be 90 degrees. If this is the horizontal, then you can yeah. Okay, so now let's see what happens when I introduce some centripetal acceleration into the system. Okay, I'm gonna look a little silly, but this is for you. Did you notice how when I swung it, it went out this way? And you'll see that this correlates directly with gravity, and then centripetal acceleration goes that way. You can imagine it as a triangle. Gravity going this way, centripetal acceleration going that way. This bag is going to be at this angle right here. Cool? Cool. All right, let's get back to the problem. Alrighty. So, as I said with the demonstration, what we're going to have is this arm, which is radius r, the bag, which is the force of gravity, which is going this way, and then, well, let's go ahead and write centripetal acceleration first. Centripetal acceleration, which is going this way, and then the force of gravity, which is going this way. Then the object, or the bag in my case, is going to be swinging out in this direction. This looks more like a that's not a bag. Okay. And the angle with the horizontal is going to be this angle right here. How did I know it was the angle with the horizontal? Well, when they say angle with the horizontal, this is the horizontal. Any angle, if you have a line that's going this way, it's going to be right here. If you have a line going this way, it's going to be right here. It's going to be between the line and the horizontal. That's going to be the angle between the object and the horizontal in this case. In this case, it's going to be this human centrifuge thing. So now that we've denoted this, let's go ahead and see if we can calculate what's going on here. Okay, so force centripetal is going to be equal to mass of the entire thing, which is going to be mass of the entire thing times, force centripetal is going to be mass of the entire thing times centripetal acceleration, which is just going to be equal to mass times v squared over radius. Okay, and force of gravity, as we all know and love, for mass times gravity, that's going to be right there. Okay, so let's see what can we do here. So if we plug in some values, let's go ahead and plug in some values. Centripetal acceleration in this case is going to be equal to 10 G's. So we can go ahead and equate this to mass times 10 times gravity. We can go ahead and write it like this now. We got mass times 10 times gravity going this way, and in this way we have mass times gravity. Well, how do we then calculate what's going on here? Well, we don't know what mass is, but this funny thing with triangles, the angle between a triangle with 100 and 200 right here is going to be the same angle between a triangle of sides 1 and 2. You can imagine dividing both sides by 100, and the angle will still be the same. So the same will be true here. We just need to divide these by some constant factor, and then we'll be able to work with those factors. Let's see, what factors can we work with? We can remove m for both sides, and we can remove g from both sides, and this will just be equal to 1. So we got, right here, we got a new triangle, 10 and 1, and we need to find this angle. How do you find this angle? Well, you'll need to use your trigonometric, is it identities? I'm not exactly sure that's the word, but you're going to be using that. And let's see, we have opposite and adjacent. So what we're going to do is to find this angle given opposite and adjacent, let's see, tangent of theta is going to be equal to opposite over adjacent. Sine of theta is going to be equal to opposite over hypotenuse, and so on. So we also have cosine of theta, which is going to be equal to adjacent over hypotenuse. Do we have hypotenuse? Well, in this case, we don't really. We can find it, but let's see. Well, we have adjacent, we have opposite, and we're looking for this angle. So we can use this one. We don't have hypotenuse. We have opposite. We have adjacent. So tangent is really our only reasonable option here. Goodbye. Okay. So what do we do from here? Hopefully, if you remember in the past, what you need to do to obtain this angle is to do the inverse of this operation out here, which in this case is going to be inverse tangent. Tangent -1 of this side, and tangent -1 of this side. And that's going to give you tangent -1. Tangent inverse of opposite over adjacent is going to give us this angle right here. And our opposite side is going to be equal to 1, and our adjacent side is going to be equal to 10, if you remember right here. So we do that, inverse of 1 divided by 10. The angle is going to be equal to 5.711 degrees. That's pretty cool, ain't it? Math works. Okay, this is going to be the last problem. This is going to be the last problem for today. If a car takes a banked curve at less than ideal speeds, friction is needed to keep it from sliding towards the inside of the curve. A real problem on icy roads. Okay, so let's imagine this. Let's imagine this really quickly, just for the sake of this problem. Let's imagine you're driving on this road, right? And you're just standing here. Let's say you're standing here, right? And this is ice or something like that. This is something with a really low coefficient of friction. What happens? What happens here? Well, your force of gravity is going to be going this way, and if you remember your trigonometric stuffs, you have a force of gravity in the horizontal direction. That's going to push you this way. And if you're driving, you're going to have the same problem. When you're driving your 2023 Toyota Prius XLE with leather seats and a hybrid powertrain that's capable of generating 198 horsepower and achieving 52 miles per. My bad. When you are driving your car, what you're going to have is the same thing. You're going to have the horizontal component going this way. And if you're staying still, your car is going to slide that way. But what happens when you are driving? When you are driving around a banked curve, I move this way. When you are driving around a banked curve, let's imagine that this is the top view. This is radius, and this is going to be the road right here. This is going to be you right here, right there, and you're going to be going at this velocity. You can see that you're going to have some centrifugal force, which is going to be going this way, force centrifugal. And what that's going to look like on the free body diagram is, well, if we draw it, force of gravity going this way, and force centrifugal going this way. Now, why isn't it going this way? Well, it is, but not exactly. You can imagine this as just a really long ball attached to this string towards the center. It's going to be going this way and not this way. And it's going to be reliant on this angle right here. And if you break this up into components, you can see that some part of it is going to be going this way, opposing the horizontal force of gravity. The horizontal component of centripetal force is going to oppose the horizontal force of gravity. So calculate the ideal speed in meters per second to take an 80-meter radius curve banked at 15 degrees. So ideally, you're going fast enough to where you are not sliding downwards and you're not sliding upwards. So these are equal. So let's go ahead and if we continue drawing this FCY, if we go ahead and draw it like that, then we need the horizontal component of gravity to be equal to the horizontal component of centripetal force in this case. So let's equate them together. Let's see, is there any other force going on here? Well, at this point, if they are equal, then there is no friction. There is no static friction, because the net force right here, as stated right here, if it's taken at a speed that is less than ideal, friction is needed to keep it from sliding towards the inside of the curve. In other words, if it's taking a speed that is equal to the ideal speed, there is no friction that is required. Friction is not present in this system at this moment. When you will have friction present is when you're driving way too fast or way too slow. So let's equate them together. FGX has to be equal to FCY. FCX. So let's go ahead and break this down. I encourage you to go ahead and try solving this for yourself really quickly. Come back in 1 second. Okay, here we go. So FGY is going to be equal to the mass of the car times the gravity of the car, and the horizontal component is going to be the opposite component of this, which is going to be sine of theta. This has to be equal to the centripetal force. The centripetal force is going to be equal to the mass of the object times the velocity squared over r, which is just going to be, this is centripetal acceleration right here. This is going to be multiplied by, let's see, the cosine of the angle, cosine of this angle. And if you're wondering how I knew that this angle is equal to this angle, if you just look at it, if you look at it really quickly, you have this bank ramp right here, and the centripetal force looks a lot like the bank ramp. This is it is quite similar. It's quite the same thing. So the angles are going to be the same. Okay, so we have that, and we can go ahead and reduce this a little bit and get rid of m. And now let's solve for, they're asking for velocity. They're asking for speed. So let's go ahead and isolate speed, or velocity in this case. So g sine of theta divided by cosine of theta times r is equal to v squared. So we just get the square root of this, and we'll have the velocity. So 9.8 times sine of theta divided by cosine of theta times radius, which is going to be, what's the radius? 80 meters, is equal to velocity.
let's go ahead and see what we could do here. The velocity needed is going to be equal to 13.8896. Let's round that to 1.389 meters per second. That's the velocity required. Let's see if we got the right answer. You know, I'm not exactly sure what I plugged into my calculator, but this is the wrong answer. When I recalculated it, I got 14.49 meters per second, which is indeed the answer in this case. Okay, so next part. What is the minimum coefficient of friction needed for a frightened driver to take the same curve at 15 meters per second? Well, given that this driver is frightened but not freaking out, meaning they're not turning the steering wheel left to right, going crazy, meaning they won't spin out, meaning they are driving straight, meaning they are okay, meaning that I should stop saying meaning so often, then we can go ahead and depict this as the following. We have this car. Same thing is going on. This angle, is still theta. Force of gravity going this way. Force of gravity x. Force of gravity y. This is also equal to theta. Oh, I almost completely forgot. Force normal. I've been neglecting you. I apologize. So now we have, we also have centrifugal force going this way, whose components look like this. Okay, so so there's a minimum coefficient of friction needed. So in other words, there's going to be a friction force in this case. Static or kinetic is going to be, well, if it's not moving, if this object is not moving with respect to the x-axis horizontally, then it's going to be static. It's going to be static coefficient of friction. How did I know that? Well, if you are sliding, if your car is sliding, right? If it's moving side to side, then your car is moving, then that's going to be kinetic friction. Kinetic friction is present when the object is moving. Static friction is present when the object is not moving. In this case, we're looking for where the car isn't sliding. Is not sliding on the ice, on the road. It's not sliding side to side. So with respect to the horizontal, it's not moving. In this case, you can close your eyes and imagine that. So, well, friction is going to oppose, which is going to be going this way. F, the force of friction. I'm just going to call it FF. Okay. I got to pause the video for a second, at least pause my recording for a second. I did overlook one thing, which is this velocity right here. This velocity is 15 kilometers per hour. And what we need is the SI units. We need this in terms of SI units, which is going to be meters per second in this case. So go ahead and convert it into meters per second, kilometers per hour. For every kilometer, there are 1,000 meters. And for every hour, there are 60 minutes. And for every minute, there are 60 seconds. Which this is going to get us. 4.166 repeating meters per second. Poor guy or poor girl. Poor person is traveling at 4 meters per second. Now I understand what they mean by frightened. A frightened person wouldn't be going excessively fast on an icy road. They'll be going extremely slow. And remember what they said earlier. If a car takes a banked curve at less than ideal speeds, friction is needed to keep it from sliding towards the inside of the curve. So this is going to be sliding towards the inside of the curve without friction, meaning that friction is going to have to oppose in the other direction, which is a slight oversight on my part. If you make the oversight in a test, it won't be the end of the world. It's likely that whatever answer you're going to get is probably going to be negative or something like that. It's going to be the wrong sign. So it's not the end of the world there. Just do be careful. Yeah. Okay, so now that we have this, let's see. What do we do? Let's go ahead and define the coefficient of friction. Coefficient of static friction or kinetic friction, let's just do friction in general, is going to be equal to force of friction divided by force normal. So we need these two things, force of friction and force normal, to calculate this. So let's see we can define force normal. Well, force normal, well, the net force in the y direction is going to be equal to 0 because it's not moving up or down, and that's going to be equal to force normal minus FGY, force for the vertical component of the gravity, minus the vertical component of centripetal force. Okay. Do we have any other vertical forces? Let's see. Scratch this out. This is going that way. This is going that way. Nope, we're good. There are no other horizontal forces in this case. So what about here? In this case, F net in the horizontal direction is going to be equal to FGX minus the force centripetal in the horizontal direction minus friction, force of friction, which is up here. How did I know to put to make FGX positive? Well, it's completely arbitrary. Just pick a direction. The F net should still be equal to 0 in any case. Your answer may or may not be the wrong sign, but you will get the right magnitude regardless, given that you do draw the free body diagram correctly and stuff like that. So let's go ahead and solve for force of friction and force normal. Force normal is then going to be equal to force of gravity in the y direction plus force centripetal in the y direction as well. Force of friction in this case is going to be equal to the force of gravity in the x direction minus the force centripetal in the x direction. And from here we can either plug it in directly or we could solve it. It really doesn't matter. We'll be solving for it either way. So I'll go ahead and I guess solve for it here. Oh dear. There we go. Okay, cool. Force of friction is going to be equal to force of gravity in the x direction, so mass times gravity times the x direction, which is going to be sine of theta, minus force centripetal, which is mass, times centripetal acceleration, which is velocity squared over r, times cosine of theta. Force normal is going to be equal to the force of gravity in the y direction, which is going to be cosine of theta, minus force centripetal in the y direction, which is going to be sine of theta. So if we go ahead and solve for both of these, we don't have m, so let's go ahead and factor out m in this case. We can go ahead and factor out m in this case. We'll get m times, so we can go ahead and remove this. I'll just move this onto the outside. Mass times this times minus that, and so on. And we'll do that up here as well. Okay, so in this case, it'd probably be a lot easier if you plugged it in directly. It'll be easier to see that you can, well, actually, regardless, you'll need to see that you'll need to factor this out. Mass times something. Whoo, okay, almost there. 9.8 times cosine of theta, cosine of 15. Minus, which I'll go ahead and put the value here, 9.4661 v squared, which is going to be 4.166 squared, divided by the radius, which is 80, times sine of 15, 0.0561, 9.8 times sine of 15, 2.536, and this is going to be velocity squared, which is going to be 4.166 squared divided by the radius 8t times cosine of 15, 0.2096. Mass times 2.3264, 9.4661 minus 0.0561, 9.41. We can go ahead and plug this in now that we have this in terms of that. Coefficient of friction is going to be equal to the force of friction, which is mass times 2.3264 divided by mass times 9.41. Mass cancels out, and what we get is 2.3264 divided by 9.41. Coefficient of friction is going to be equal to 0.247. Pretty darn close. Thank you for watching. Go take a nap, eat an M&M, something like that. I'll see you guys next time.